All right, 2 minutes and a bit till day 10. While we wait, I wanted to go over solution for day 9 real quick. So I finished with something like this where we get the result, but the takes about 12 seconds or so. I did profiling, and the slowest part was this one, which makes sense. This is the part that looked for a gap to fit the file into. This is for part 2. Part 1 was also slow, took about a second or so, at least for me, and it just kept moving one file piece one by one. So I rewrote it later yesterday to have the solution. It runs 200-ish milliseconds, 300 under 300 milliseconds. For part 1, it moves the whole thing at a time in one lip, so it just reverses the end essentially and puts it where there is a gap in a file on disk. And for part 2, we keep 2 arrays in check, gap sizes and gap indices, and this allows for quick find of the gap to fit, right? So once we know the size that we have for this object, for this file, we check everything from that size up till 9. This is what this does, up till 9. And we check for that in the gap sizes. And if we find something where it's not equal to the size of the gap sizes, then we do the same thing as before. We remove it from the array, reset it to 0. Set it in the new position of the gap index. And we also need to update the gap sizes to now be smaller by size. It's now smaller, it could be 0 now. And I also move the gap index further by 1 because now the gap starts later on because it's been, we took a size chunk from it. That's it. Pretty straightforward. All right. Oh, and we're ready to go. Ready to go. Sheet 10. Boom. All right. The 10 txt now. Ooh, interesting. I bet this is a map. Okay. T index. Yeah. 1 to 3. Okay. You'll arrive at the lava production facility. You begin to search, or others begin to search search the complex. You feel a small nose boop your leg and look down, discover a reindeer wearing a hard hat. Reindeer is holding a book titled Lava Island Hiking Guide. Alright. But it has been scorched by lava. You plan to ask for help, but the reindeer brings a topographical map. That was oh yeah, okay, that's the one that shows the rivers and mountains and things. As you're about to ask how you can oh no, or how to, okay, okay, perhaps you can help fill the missing hiking trails. Interesting. The topographical map indicates the height. Okay, so 0 is lowest, 9 is the highest, so there's a peak here. Okay, based on unscorched scraps of the book, you determine that a good hiking trail is as long as possible and has an even gradual uphill slope. That means that a hiking trail is any path that starts at height 0 and ends at height 9 and always increases by the height of exactly 1 each step. Hiking trails never include diagonal steps, only up, down, left, right. Okay. Trail head is any position that starts one or more hiking trails. Here, these positions will always have height 0. Okay, so we start at 0. Assembling more fragments of pages, you establish that a trailhead score is the number of 9 height positions reachable from that trailhead via a hiking trail. In the above example, a single trailhead in the top left corner has a scope of 1 because it can reach a single 9. The one in the bottom left, okay, this trailhead has a score of 2. Yeah, okay. So from 0 to 9, it has a score of 2. Number of 9 height positions reachable, okay, from that trailhead. Right. Yeah, so we can go 1, 2, 3, then 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9. There's actually 4 ways, right? Because they all interact at 5. There's a 5 right here. Interesting, sneaky. Okay. Okay, in this case it was down, right, down. Maybe this is better. Okay. This trailhead has a score of 4 because every 9 is reachable via a hiking trail except the one immediately to the left of the trailhead. So there's 1, 0 right here, and we can't go here, but we can go to down, left, no wait, 3, 4, 5, yeah, okay, I mean, 9 here, 3, 4, 5, 6. There's 2 ways to reach this 9. There's 1 way to reach this 9, and there's a bunch more 9s. Okay. I guess if you can reach it, you can reach it. Okay. So this is 4 because every 9 is reachable, even though some 9s are reachable many different ways. We can reach 9 down. Okay. This topographical map contains 2 trailheads. Yeah. So each, okay. So if we take all of the zeros, then from all of them, we look for all the ones. Okay, so this is like, we can do breadth first search, maybe. This topographical map contains 2 trailheads right here. We start at 0 and we finish at 1, 9. And we start at 0 and we finish at, well, whichever 9. At the top, that's score 1, while the trailhead at the bottom has a score of 2. What's a trailhead again? Trailhead is any position that starts one or more hiking trails here. Okay, at 0. Okay. So trailhead at the top has a score of 1. And this one has a score of 2. 1. So because 5, 6, 7, 8, 9, 7, and then we can't go down, so it has to be up. And this one has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here's a larger example. This larger example has 9 trailheads. Considering the trailheads in reading order, they have a score of 0. Okay. Adding the scores together, the sum of the scores of all trailheads is 36. Okay, so for each starting from 0, we need to count how many 9s can be reachable by that. Okay. What if we go in reverse? Because this is basically dynamic programming problem, right? Because we start at 1, 0, right? And then we go and find all the 9s that we can reach. But then we look at all another 0, right? And we find that it will, find a bunch of 9s, new 9s, but it might also get the old 9s. Now, if we start at 9s instead and go down till 0, keeping track of all of the unique 9s, right? So 9 there. Would that work? I'm gonna try that way. Because we still would need to. Yeah, I think that way is better. That way is better. Yeah, and we do 9 steps. Let's try that one. Okay. So we'll use this one. Is there a smaller example? Let's use this one. It's not a real input. We just get rid of yeah, there's going to be a bunch of 10s. So this is our map. The map equal to 9. Yeah, these are all the 9s. Get all the indices from it. Okay. How big is 10txt? It's going to be 45 by 45. Okay. Now we need to find all the 8s. So these are positions of the 9s. Okay. I really don't want to do this checking if it's within bounds. It would be nicer if we had all of the iota 9, iota 10. Let's do iota 3 for now. And for each m equal that indices. Okay. 5. Yeah. 10. So this will be our indices. So just for me, P n is all positions of n in map. Yep. Okay. So now, which we can just start with P9, right? Same thing. Same thing. Yep. So now we want 8, right? So P plus, we want to keep track of numbers. Yeah, we don't need an 8 because we can just check just one of them. I will have a 1, okay, here. That will say we can reach all these 9s one way, right? So we have positions. This is how many of each there are, right? Then just one. It will be like really like 1. At some point we'll say, oh, this 9 is reachable 2 ways so far, etc. I think. Does that make sense? Yeah. Because at some point we'll get to a 6, for example, and we'll say, okay, there's 5 ways to get to the 6 from 5 different 9s. Right? Yeah, so we want to keep a count, so we'll keep that as a alpha 1, but it will be like replication matrix instead. Then these are the positions of 9s. We'll take the first one. We'll look it up in the map, see what it is. What? I don't like this. What? Close. Okay. One take from map. All right. So this is subtract 1. So that will tell us the next one. We will take for each position. We want to do the directions. Yeah, I guess directions. Call capital D. 1 0 0 1. I can't even 0 1, and then same thing but with negative 0 1. Okay, so plus dot D plus iota out plus. So these are all the positions. maybe I should do alpha D, yeah, and I don't know. So we want to flatten it. How do I flatten it best? I presume. What if I just let me try without unique? Because how big can this be? This might be big. Yeah. Let me try it without unique. Just actually counting the positions. So we do this. Doesn't matter. And then are there any uniques? Let's just check. Yeah, there are some uniques. And non-uniques. 4, 5, 4, 3. Let me just find them. Sorted. Yeah, there's 0, 5, 1, 6, 0, 5. Okay, so let's take a look at 0, 5. So we intersected with positions on the map where n-1. Does that work? No, that doesn't work because it needs to be disclosed, which is annoying to me. We'll disclose it. Is it unique? How's it more? No, it's not unique, it's intersect. It's intersect. Why is there nothing? Why is there nothing? We have two arrays. This will tell us, oh, I already did n-1. Ugh, okay. Yes, okay. So from here, there will be 1, 6. Now, 1, 6 is mentioned twice, 3 times. 3 times. Yeah. Wait, why is it? Oh, -6, -1, 6. So there's 0, 5, 0, 5. Okay, that's not in the next one, but there's 2 1, 6s. 1, 6s. So I want to make sure that if I do the intersect, that it doesn't work. There's 1, 6, but I actually want to keep all of the. Yeah, there you go. There you go. We don't need this third sword anymore. So we can get to from 8. We can get here in this many ways. Yeah. Yeah. All right. So seems easy enough. All right. So that's the next one, and then we recurse. Now at some point, if n is equal, no, n equal to 0, done, I don't know. Okay, we get to 0. Now in our case, so the next one is 0, right, is what we're saying. What do we have so far? A bunch of 1, 3s. Okay. Yeah. No, something's wrong. So 1, 3, 1, 1, 3, that's a 9, eh? What? Let me just print. This 1, 3 is, no, I think we ran out of things here. So we start at 2, 0, 2, 0. Let's actually look at the map at these positions. Yeah. Okay, yeah, that makes sense. So we found all the ones. Next one is 0. Now we need to find 0. But something's wrong. There are many ways. What's our map again? This one. Let's keep it simple for now. So we start with 6, 6, 0 and 6, 6, 5, 0, 5, 6, 4, 0, 4, 6, then 3, 0, 3, 6. Then we're supposed to move in 1 and 5, 2 and 4, 3 and 3, right? So there's still, we're keeping track of all of them, right? Now 2, 3. Okay, I see now. I see the problem. Yeah, we're not. All right. Yeah, no, this was not right. What instead we'll do is we'll start at 0. We'll go up. We'll go up. I think it's better. We'll go from the bottom, right? Just double check here. What happens here? Okay. And then we'll actually do a each, right? Yeah, okay. So start at that 0 position and we see how many 9s we can reach. Let's do that that way, yeah. And we'll just memorize or something at some point. Should be doable. So the plus here. Input 1 take W. Okay, see. We want to keep them as arrays. Now we want to each enclose. Yeah. 1 take. So weird. Yeah. Okay, 1 take. Take a look at that in the map. All right. -1. No, plus. So we start at 0 actually, right? 0. So +1. That's next. Yeah, I already have that. If next is 9. Not yet done. Well, it'll fail, right? Well, then for n, no, we don't need this anymore. Then we take a look at input yot out plus d sort. Don't sort, and interact with the first with the disclosed of pn. Yep. We can also, I think, do n taken. Yeah, same thing. Yeah, and we recurse down. 5, 6, and 5, 0. Yeah, okay. Next one is 9. Let's do this one instead. Wait, what? No, let me find this one's better. Yeah. So there should be, yeah, one has a 2, one has a 1, one has a 2. Yeah. 4, 3. So we got to 9. 9 is next. So then let's get to 10 first. Yeah, let's try to get to 10. 5, 3, 5, 4. Right. Yeah. 10. So we're saying, hey, we have a bunch of 9s. We visit a bunch of 9s, and we want to do a 10. I think I just need to count 1 and 2. If I use this input, oops, there should be 20, 24. What? How is that possible? It's possible because we should be doing it with like this. Yeah, this way all the, yeah, there you go. So the problem was that we had duplicates, and if we flip it around, then this one doesn't have duplicates, so the result doesn't have duplicates. So we deduplicate as we check. So now 5, 6, 5, 3, 1, actually in exactly the same order. Yeah, makes sense. And we'll sum it up. 36. Let's try on production input. Let me print n as we go. Oh, that's pretty fast. It's pretty fast. 517. I was trying to optimize and stuff. Yeah, okay. That was so fast. All right, well, let's take a look at part 2. The reindeer spend a few minutes reviewing your hiking trail map before realizing something, disappearing for a few minutes and finally returning with yet another slightly charred piece of paper. The paper describes a second way to measure trailhead called its rating. Trailhead's rating is the number of distinct hiking trails. We just flip things around, equal to this, and then I can, since we're using n, like this, yeah, and that's something like that. Yeah. Okay. The paper describes the second way to measure trailhead, called its rating. The trailhead rating is a number of distinct hiking trails which will begin at the trailhead. For example, you start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Its rating is 3 because there are exactly 3 distinct hiking trails which begin at that position. Yeah, 1, 2, 3. Isn't that the same thing? Is that what we did before? Okay. Number of distinct hiking trails. Right, because if they... Yeah, so this would also be 3 in my case, right? If I went here, it would also give me 1. Right, because of this. But if I change the order, I did... No, not this order. If I flipped this around, same thing, 3. Yeah, so we're not doing uniqueness anymore. Is that it? Here's a map containing a single trailhead with 13. Okay, is that it? I'm gonna try this. Here's a larger map than before, from before. This is the one that gave us 27, right? 36. So 36, 81. Dude, that's it? Okay, now it might be slow, so let's check. No, it's not slow at all. My God. What? That's it. Okay. So we just flip things around. That's embarrassingly fast. So the only difference, so we always start at position 0 and we go up. So don't need to memorize, don't need to optimize in any way. My goodness. Yeah. So we'll look at the next position by taking a look at the first one, looking at what is in the map, adding 1 to it, and that gives us the next number, right? So if we're looking at 0, then we check, oh, we're looking at zeros, so the next one has to be a 1. If we got to a 10, right, then we just return the number of unique positions, right, that we've been tracing for each of those starting heads, trailheads. Then we recurse, and in the first option we go through, I mean, in both cases we do the same thing. We look at what's available even for the next one, right? So this P is basically memoized, kind of a cache of all of the positions for that next point. And this is given W, alpha, omega, which is a starting position, which is the current position that we're tracing, right? We do the outer product with all the 4 different directions, up, down, left, right. And if we, what is that called? Union versus intersection. Oh, can't even remember that. Intersect. So we intersect with the numbers. Now the thing with intersect is it will, if the left part is unique, then it will return unique numbers. But if the left part is not unique, in this case it will not be unique, because there will be multiple ways to reach it, right? It will not be not make the result unique. So I will just make sure to keep the things on the right. That's all it does. So here we're returning a unique set of ways to get there, because we don't care about all the different ways. We just care about the unique ways. In fact, we can process it once. I believe we just make it unique, and then, yeah, okay. We don't even need to do it once. Yeah. So, in fact, we can run only once. Trails will be this, right? Now we'll only process it once. Slow, doesn't matter. Then we unify each trailhead, unify and count, and add up, and this one will be just count. Yeah, okay. That was kind of easy. Or I don't know, did I accidentally benefit from APL here? I mean, I did. The dot outer product was easy for me to do, but that's just a for loop of 4 directions in any other language. I did have a cache of all of the positions, but even that I feel like is pretty straightforward. I don't know. I really don't like this part. It looks off. Looks kind of off. I don't like this one being capitalized for no reason. Yeah, seems simple. Just move up, down, left, right. I don't know. By the way, can I, for the map that we have, I use a key. What does it return? Ah, the key will be by row. Never mind. Never mind. Yeah. Well, many other ways to optimize it. We could optimize, we could memoize, but I don't know if it makes sense. I was thinking of going from the 9s, but apparently could have been potentially usable. Go from 9s, could have been done, but going from bottom up works. Yeah. Yeah, I don't really like this one because what if it's empty, right? What if I call this fancy function, well, for now, will take P0, for example, right? And what do we do? Close each on disclosed P0. Wait a second. First of all, I think this, I really don't like this business. I don't know. It seems stupid to me. But maybe, I don't know. So first of all, that's same thing as taking, there you go. So right away, we can get rid of this, make it a little simple, same thing. So we get that, then we need to enclose close each, right? Because if I run it for each one here without anything, it'll give me, it will work the same way, but at this point I will get, like, I won't be able to do the W product with D. What will it return? Yeah, right, Modi. Now it works. It works because that's not the way. That's not the right thing. There's not 2 by 2 ways each to get from, no. Yeah, these are simple arrays. This array of 0, 2. It's not list of positions. I need to make it list of positions. So I need to enclose each and then run my function each. So that's why just do iota here. Yeah. One take. No, wait, what? P. Sure. Sure. Yep. Pretty straightforward. What is my... How are people doing here? A lot of people are giving up. Why is this one 900? No way. No, that something's wrong. Right, okay, yeah. Because everyone who solved part 1 basically solved part 2 as well, because it's the same thing. 5,000, and what was my score? 4,000. Yeah, Leaderboard, day 9, 1 minute, 38 seconds for both stars. Now, I don't believe that, but still. Maybe. Okay. Yep. Seems easy enough. Easy enough. We could also potentially speed it up if it wasn't already so fast. Yeah, it's fast because there's only 9 steps that we're doing in this loop, right? There's a lot of positions, but just 9 steps. Yeah. I don't know. I'm kind of. I mean, I'm glad I finished on time and everything within an hour, but it feels a little underwhelming. Okay. So, by the way, if you write APL, this is something that I do, which is if I have a simple function, I just start writing the function itself. But if the function is something that has a block inside, like our separator inside, so it's multiple things, that means I always start the function if I put it in one line with a space there. That means, hey, this is a more complicated one. So that means don't just go to the end of the function and start reading it, because that's how you would potentially read it, something long. You start at the end, try to figure out what the hell's going on here. But in this case, hey, be careful, look for blanks and breaks. So we actually start here. Actually, we start at a colon, and then so we go right to left. Okay, so that's n is the next number. If it's 10, then we return things. Otherwise, take n next numbers from the positions and intersect it with our set of things and recurse. We could optimize it, right? We don't need to do that. We can say, hey, start at 0, right? Does that still work? Yeah, 81 alpha, right? Well, we'll start at 1. How about we start at 1? And we don't need this anymore. That's just our alpha. And we don't need this anymore. That's just our alpha. And here is just alpha plus 1. Does that work? Yeah, works. A little cleaner. So we start at 0 and close each and run this for each. I really don't like this part, but maybe I'll replace it like this, just cleaner. Close each and run this each with 1. With each, 1 just gets replicated, so we get a 1 for each time we call this function. That's fine. Yeah, I think that works. Can I make it? I don't know. Anything else? No. I think that's as simple as it can get. Maybe we don't need even this. I don't know. P equal, wait, no, not P. Map equal alpha, iota. Don't need P. Equal iota. Let's call it an M. Let me run it. Yeah, that optimization did nothing. Really? 200, what's the fastest I can get? Nah, 195, 194. Okay, let me just go back to the original one. Sure. 188. All right, it's slightly faster. 153. Oh no, 553. 50 milliseconds. 135. No, this is faster. Okay. Never mind. I will keep it this way. Okay. Put a space in there. Wait a second. That's because no, we get no benefit. We get no benefit from that. 160. No, we do. 166 is how fast we can get this done if we use the memoized positions. Yeah, all right. Not significant. I would even simplify it, but maybe it's fine. I don't think I need a comment for this. It's pretty straightforward. Yeah, I thought they were gonna have some like complicated traversals. All right. 10 in. What is happening here? Why is yeah, that was weird. Okay. Commit. Boom. 10. Is there anything? Don't need this here. That's speeds it up a lot. 100 milliseconds, and it only like if I have an empty file here, right, or file that just reads input. That's 94 was the fastest milliseconds, right? So let's see. Going up 115 is the fastest. Yeah, so it adds like a lot. There you go. I think that's as clean as can get for me. Directions. Oh, we don't need this anymore. That was just a hack for weird input. The digit index in the thing. Boom, bam. Do we even need to process it, actually? We don't need to process it. If we do it like this, and this will just be digits for each of the digits. Yeah, still the same thing. Yeah, so we check for each of the, characters of the digits. Yeah, okay. But it's still like integer based, right? So we still look for 0th element of p. Yeah, so that works. I don't know. That seems fine. I don't think there's anything else I can do here. I need to do the outer product. I need to look it up in the next array. I need to do this. It would be nice to get rid of this stupid business here. I hate it. We only run it once. Gotta keep directions, right? There's not much I can do about this one. Maybe, I don't know, maybe optimize it, but it'll just make it like I can write APL code that will generate this array and it'll be shorter. But what's the point? It will look ugly. Do I need a space here? Yeah, I do need a space here. All right. Yeah, all right. Yeah. Now 10 2024 10 push, and you'll see not the 7th but the 10th. Where's that? Yeah, yesterday was the longest so far, 500 bytes, less characters, but because these are Unicode characters, a little longer. Yep, 200 bytes. I'm not optimizing for size, but I want to keep it as small as possible. Cool, cool, cool. What else? Let's take a look at other things people have done here. Oh, this is something funny for part 2. When your first attempt at part 1 solves part 2 instead. Well, I wouldn't know. I might have solved part 2 earlier. I probably did because I did have it replaced that way. But how would I know? It ain't fast, but it's honest code. 5th nested loop. Oh, this is for part 9. Okay. Part 2 planned. Yeah, yeah. Oh, Control Z meaning like Command Z for me, which is undo. Undo will get you the. Yeah, funny. All right, what's this one? Oh, this is the defragmentation one. Okay. Cute. Yeah, alrighty. Let's open up a bunch of these. Me trying to solve an error. Error doesn't happen with debugger. Okay. Okay. I'll be interesting if a later day, just talking about this one, it would be interesting if at a later day we will have something that will involve defragmentation. That'd be interesting. Like, but more complicated, like Tetris-based defragmentation. All right. Real test. This is what, for day 9? Oh, look for a hint. Okay. All right. Okay. Yeah. Let's see. Yeah. Yum, 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 yum. Oh, another visualization for the defragmentation. Let's run it. Oh, yeah, okay, cute. I've never done this one. I don't. This one. Maybe. No, this is for DOS or something, right? Yeah. Anyway. Super cool, yes. Let me guess another. Oh, you actually. File size 123. What? You choose a color. Oh, that's pretty cool. This is really nice. Dude, this is console. Is it console? It's not console. Can you do console? No, you can't do console like this. No. You could click around, but you can't like, maybe you could. It is terminal. It is a terminal one, yeah. I thought it was like JavaScript at first. Anyway, I'm not reading this. Okay, let's take a look at solutions. That one's probably show all 119. Let's look at the best ones. Why don't we? Yeah. Oh, okay, and they use the complex numbers. Fine. And then, yeah, you can also do it like this: iota minus iota minus 1 plus 1. All right. And then, how do they do part? Right, in part 1, they have trailheads for trailheads. Otherwise, the call gets, okay, they traverse again, but count distinct paths. So, okay, all right, yeah. Could just do that and then unify, do unique. DQ, that's what we did, right? Visited, okay, that's complicated. Visited, why do you need visited? Don't need any of these. Add, start, part 1, part 2. Yeah, okay. Anything interesting? Go, Java, F#, Rust. Python, Go, F#, Python, Rust, Julia. NIM, interesting. Ooh. Python, C++, Java, D, Python, Haskell, Mathematica. Whoa. Graph, dude, what the hell's going on here? Yeah, he did a dot outer product, I guess. Plus column, I don't know what's happening here, but given the positions ij, I guess it does at least for one. Oh, given a list, is it just, the hell is a list? Dimensions list, and I don't know what's happening here. Yeah, I don't know. Python, Rust, AMD C++. The hell is AMD C++? I'm doing Advent in my own programming language. Pretty happy. I got up a bit. Okay. ND as an NDC. Okay. And what is this language? Let's. Okay, that looks like, doesn't look like. What do we know? C. Okay, so he has implicit queues or sets, I guess, or arrays. I guess sets. Nice looking language. Python, Julia, Python, Go, Kotlin, YACTL. YACTL is the JVM based Python, Ruby. Even, why is it so big? Why is it so long? All right, Haskell, C, Jai. Yeah, everyone's solving part 2. Start, Python. That's it. Okay, so no APL yet. Let me go through the previous day, see if there's anything that I missed. Let me just load up all 500. My goodness. APL. This one. Oh, what happened here? What? Maple, no. Weawa, I think I saw. Oh, there's new Weawa. Okay, no variables, just do things on a stack. That's the problem I have with Weawa is like if I'm here, I have no idea what I'm working on, right? Like at this point, I don't know what's on the stack, so I have to go from all the way from the beginning, try to figure out what I'm trying. Now in APL, you could also get the same situation if you have a long list of verbs, but even then, it's doable. Okay, I think there was at least one other Weawa. I don't know where I went. NGN? No NGN. It's BQN. No BQN. Come on. I'm sure somebody did it, just didn't. Didn't post it. That's fine. All right. I think that's it. Thanks everyone for joining. I don't know. Thanks everyone to joining. Oof. Let me check real quick here. Who was Basher, where are you? Advent of God, check. I don't know what happens here. Maybe. Yeah. Raid. I'm gonna try it. Never know. I have to go someplace. I have to go to my own stream. Alright, that's fine. Okay, then thanks everyone.